Number 88 in a classwork for analytic geometry asks to prove that the two triangles OPM and ONM are congruent isosceles triangles. So we also have to conclude that they're isosceles triangles. So first of all, we have coordinates of vertices O and M. So this is just from given information, so given from the graph. Now at number 2, we apply the distance formula. So OP, so the length of this segment is given by the distance formula, which is, so change in x is 3 minus 0 squared plus 4 minus 0 squared. This will be 3 squared, which is 9, plus 4 squared, 16, giving us square root of 25, which is 5. So OP is 5. PM, so PM, there's no change in the y-coordinate of M. It's just the horizontal shift. So this is 5 units to the right. Now MN, so the distance of MN is given by square root of change in x, which is 8 minus 5 squared, plus change in y is 4 minus 0 squared. This will be the square root of 3 squared, which is 9, plus 4 squared, which is 16. So square root of 25 is equal to 5. So MN is 5. And also NO is just another horizontal line, which is of a length of 5. So we have that all our segments are equal to 5. Now OP, PM, MN, and NO are all congruent. We can say that because of the definition of congruent segments. Now we have number 4. OM is congruent to OM. So this diagonal line going through the quadrilateral is congruent to itself. So that's just by the reflexive property. Now number 5, OPM and triangle ONM are isosceles triangles. So this is given by the fact that two of their I guess shorter sides, because it's not the hypotenuse, the two shorter sides are equal to each other in length. So that's just definition of an isosceles triangle. Definition of isosceles triangle. And then number 6, we can say OPM is congruent to ONM. We can do this by SSS congruence postulate, because we proved that all their corresponding sides are congruent to each other. So that is why we can use SSS